Okay. We're gonna get started. I forgot to mention yesterday that I posted the announcement the day before, hoping that people saw that I extended the deadline of homework 3 that would have been due last night for a week to allow you to decide to prioritize what you need to prioritize this week, knowing that there's 8, that you might get more out of working on homework 4 than working on homework 3 ahead of that. So I am very much okay with that in the short term, but the other important part of that announcement was that anything you submit by Monday night will be graded before our exam a week from tomorrow. That anything that you do not submit, I can't guarantee you one way or the other before the official Wednesday deadline. So I'll let you prioritize what kind of feedback and what you want to work on or what's important to you right now. Questions on the upcoming schedule? Study guide should be released tomorrow for the exam. I would say for everybody else, you're probably focused on the 8 between now and then. So even if I release a study guide, it's probably not going to be particularly helpful before everyone goes. Darn it. Can't say what I was going to say. That's fine. All right, last time we had talked about the concept of Hanoi. Do we want to, let's dive into actually solving Hanoi, and then we'll kind of come back to analyzing recursive problems in a bit more detail. Was anyone able to give this an attempt? Did we have a chance to work on this since yesterday? All right, so if we're going to work on Hanoi, we need to figure out what a reasonable base case is, what the recursive case is, and see if we can structure a solution to this. So what is a base case for towers of Hanoi? Yeah.
Would it just be take a whole stack, move it to the end?
That's going to be a recursive case. A good idea. So the base case is solving a towers of Hanoi problem of size 1. How do we solve a towers of Hanoi problem of size 1? Yeah, there's one disk. You move it from where it is right now to the place where it needs to be. Base case, that's it. The recursive case is now going to be breaking down a towers of Hanoi problem of a larger size into its associated steps. So how we're going to think of this is, let's draw out a quick towers of Hanoi problem. We're going to identify our 3 rods as our from rod, our to rod, and our helper rod. And we're going to have, I'm just going to draw this as a triangle for the moment. We have some problem we want to solve. And to solve this problem, it really is just a couple of steps from the perspective of this problem. We're going to break it down into, let's say that this is a towers of Hanoi problem of size n. We want to break it down into a towers of Hanoi problem of size n-1. If we can figure out all of the associated steps with regards to a towers of Hanoi problem of size n-1, then we have the solution, the recursive solution to this. So the recursive case to this is going to be to take everything that is, aside from this base, this largest disk that we have, we want to move everything from the from rod to the helper rod. So we're going to solve the entire n-1 problem where this isn't the helper rod, this becomes the to rod, and this becomes the helper rod from the perspective of a problem of size n-1. And if we do that, then we can move this entire larger block from here to here. And leave us with just the largest disk that is here. Do we agree that when we completed that Towers of Hanoi problem, that is what it would look like? We're not specifying the steps of the solution to a Towers of Hanoi problem of size n-1. But if we could solve that problem in some arbitrarily complicated way that we don't need to worry about from this perspective, then, so that would be the first step. Step one. Move top n-1 disks from rod to the helper rod. Then step two would be to move the largest disk, the nth disk, from rod to the to rod. So that would be the equivalent of moving just this bottom disk here. And we can do that in a single move. So this is something that, from the perspective of this method, we can accomplish. After this magically happens, we can do this. This is a legal move. Then we again want to do some abstract concept. So step three is going to be to move this entire triangle onto the to rod from the helper rod. So it's exactly like step one. The helper rod to the to rod. So basically, this is the three-step procedure. And this is going to be a base case, or one of these is going to be a base case if n is of size 1, meaning that there are no n-1 disks to move. The largest disk is that base size 1 rod, or base size 1 disk that we can move, and then we have nothing else to do in step 3. So the base case is there's just one thing to do in step 2. So that's how we're going to consider this to be a recursive problem. When we do this, when we call this recursively, the new to rod, as we said, is the existing helper rod, and the existing to rod is the new helper rod. So we just flip those ideas as we now try to move. This is not going to exist anymore. And from now this perspective, now we've changed this to when we have this to move, this is now our from. This becomes our helper. And now we want to move all of this to actually, I think this becomes the to rod that we want to, the to that we want to move it to. So that we can take this and move it here. So let's see how this works in practice. Does this idea of breaking this problem down into its recursive steps make sense? So you're taking the concept of solving a Towers of Hanoi problem with size n and breaking it down into how do we solve this in terms of a problem of size n-1. You're not worrying about solving the problem of size n-1. You're just saying, let's think about this problem in terms of the size n-1 problem. So that's the logic that we're going to implement. Let's go see how it works. All right, so we're going to make a column here. parameters we're gonna need to this function. So we first need to know the size. So the size of the stack of Hanoi. We're gonna need to know what we need to call the from rod, the to rod, and the helper rod. I'm going to use characters to represent this. Because when I print this out, I want to print a list of instructions. So we're going to say that the from rod is going to have some character destination or designation. We're going to then pass in the to rod, and then we're going to pass in the helper rod. And let's break this up somewhere where we can see the whole thing. All right, inside of this, we first need to figure out what in general the first thing we need to do is. We need to identify if we are in a base case. Or we need to figure out the recursive case. Which one do we want to do first? I think the base case is probably easiest enough. So we will say if n is 1. The size of the current problem with Hanoi is 1. Then the only thing that we need to do is take that smallest disk and move it from the from rod to the to rod. So we are going to print out take disk 1, the smallest disk, from rod. And now we need the name of the from rod. To rod, and then we need the name of the to rod. And that is the entirety of what we need to do. And I'm going to again move this onto 2 lines so that we can actually see it. It's just a little bit better. And we can just return. Because we've done everything that we need to do. And since this is a void, we would just be returning to the size 2 problem that called the size 1 problem. Saying that we successfully moved disk 1. Now we're ready to execute the recursive case. So those 3 steps. This is going to be done in 3 lines, basically. All it's going to take is a single line for each one of those steps. So now we're in the recursive case. We know that n is not 1, it's larger than 1. We want to first make a recursive call to this function with size n minus 1. We need to get that large triangle, except for the base, the largest disk, to the helper rod. So that is a call to Hanoi. The new size of n is the current n minus 1. The from rod, where we are starting from, is the same from rod as our from rod. Because we have a large stack at the from rod and we want to move it all to the to rod. To do that, we need to move the triangle on top from the from rod to the helper rod. So the new from rod is the same as the old from. The new to rod is the old helper rod. And the new helper rod is the old to rod. Does this make sense? Does this call make sense? Yeah, I'm going to go back to it once we are done to be able to say we have, I can kind of draw this on the side. We're in the recursive case, so we have that big stack we want to move. This is the from, this is the helper, and this is the to. So we want to take this shaded triangle and we want to move this onto the helper rod. We want to take this and we want to move it here. So to accomplish this, this is a sub-Hanoi problem, right? if you can think of this, this is like if we took these two rods and swapped them. It would be like solving a Towers of Hanoi problem of size n-1. We need to take this stack and move it to the 2 rod. Except from the perspective of this problem, the 2 rod for this sub-problem is the helper rod for this problem. We want to get this here so we can put this here. But this is exactly the same problem as a Towers of Hanoi problem, where we have exactly this same smaller triangle and we want to get it here. Right? Do we agree that this is the same problem? Just with a swapped perspective of which is the helper rod and which is the 2 rod. So by calling Hanoi of size n-1, this is size n, this is size n-1, the from rod stays the same, the helper rod switches. So the new 2 rod that's going to be passed in as a parameter is the existing helper rod. The new helper rod is the existing 2 rod. So there's an equivalence between these 2 problems. And we just have to show exactly what that equivalence is in code. We're just saying, solve this problem. When we solve this problem, we will have moved this here. When we return from this recursive call, it's going to be magical. It's just going to happen. Although, of course, if you break it down into trying to analyze that problem, it looks exactly like this problem. Once we're done with that, we want to move the nth disk, that largest disk. So we need to print out the instruction for how to do that, because it's something that we can do. So we want to take disk, and now instead of hard coding 1, we want to say disk n. From rod, and now where is the from? Which rod should we have here? Where is the nth largest one? Yeah,
Still in the front.
still on the from rod. Yeah. Now, where do we want that disk to go? Where do we want the largest disk to go once we've moved the smaller triangle out of the way? The 2 rod, yes. We want to move it to the 2 rod. So we will call that good. And we can again break this in half. It's not to move on to the next go. That works. Now we need to move the triangle that we moved onto the helper rod onto the 2 rod. So that's going to be another recursive call because we don't know how to move an entire stack of objects. So this is another Hanoi problem of size n-1. Where is the from rod this time? Where is the location of the triangle when it starts?
Helper.
It's on the helper. So the from rod is now the helper rod. Where is the 2 rod? Where's the destination we want them to end up? The 2 rod, the destination of what we want, it's starting on the helper. We want to get it to the 2 since we've already moved this over here. So we want to start from here, get it to here using this as our helper. So the 2 rod is still the 2 rod, but the helper rod is now the from rod. So if we do this, then we have taken everything but the largest, moved it to the helper, the largest to the 2, everything else to the 2. That solves the problem. Of course, how do we know that this works from the n-1 perspective? I'm saying that it works magically, but if we were to break this down and actually look at it, what would that look like? Well, this is now, from this perspective, our from rod, our helper rod, and our to rod. So how do we break this problem down? Well, now there's going to be a new largest. And we now want to get it to the old helper rod. But from this perspective, now we're calling this the helper rod and this the to rod. So it's exactly the same problem. So this same logic is going to work to get this entire thing over there. We just take everything that is smaller than the largest disk, move it to this perspective's helper rod, which is not the same perspective as this perspective's helper rod, but we make that move, we make this disk, we move it to the to rod, and we move everything else from the helper back to the to, we'll be done. But we don't have to worry about what it's called from this perspective, because it's our own instance of the problem. We have our new names for a helper and a to rod, so we're really just manipulating what we're calling each one of the rods from the perspective of the problem. Does that make sense? How are we doing with this? Set of thumbs just for the basic idea of how this works recursively? Yeah, we're kind of at a lot of us are at a level. Let's see it work. And then we can kind of run through it with a smaller example maybe. So this is the entirety. This solves Hanoi. It will print out the instructions for an arbitrarily large Hanoi problem. We are done. Aside from writing the main that will test it. So what is this going to look like? Let's set an n. We'll start small so that we can see it work. Then we want to call an initial Hanoi. We're going to pass it n, the size of this problem. And then we just need to name our rods. So the 3 is the from, the to, and the helper. So I'm going to name them. A is the from. C is the to. These are characters, not strings. And B will be the name of our helper. We run this and we're going to get the instructions for how to solve a Hanoi of size 3. Let's see if it works. In fact, what I can probably do is it says take disk 1 from rod A to rod C. So here is disk 1 from rod A to rod C. Take disk 2 from rod A to rod B. Take disk 1 from rod C to rod B. Take disk 3 from rod A to rod C. Take disk 1 from rod B to rod A. Take disk 2 from rod B to rod C. And take disk 1 from rod A to rod C. I didn't do anything myself, I just followed the instructions. And it solved the towers of Hanoi of size 3. Do we buy that it would solve a larger towers of Hanoi problem? If we make this 7 and run it. Here's a list of instructions. This will take 127 moves. We think there are 127 lines that were printed here. There look like there are about 127 lines of instructions here. We see about halfway through, we move disk 7 once. We would expect this to be like this, right? 1, 2, 1, 3, 1, 2, 1, 4, 1, 2, 1, 3, 1, 2, 1, 5, 1, 2, 1, 3, 1, 2, 1, 4, 1, 2, 1, 3, 1, 2, 1, 6. There's a pattern to exactly what we are doing to solve the problem, but it tells us exactly how, and at the very end of this, the last thing we do is move everything onto rod C. This does in fact work. It breaks down towers of Hanoi of size 7 down into towers of Hanoi of size 6. So to do this, we are going to first solve this towers of Hanoi of size 7 problem, and I should probably get rid of the last drawing that's on the screen, so we can actually see this. The very first thing that our code tells us to do for towers of Hanoi of size, I'm actually gonna break this down now into just the 3 problem. So that we can run this code next to exactly what's happening in towers of Hanoi. So let's run it again, see what's happening from a code's perspective. So now instead of just following along the printed instructions, we're gonna follow along what the code is telling us to do. So we come into a towers of Hanoi of size 3 problem and we say, is n 1? No, n is 3. So the first thing we're going to do is we're going to call Hanoi on size n minus 1. Except we're going to swap the positions of these 2 rods. We're going to take them and we're going to kind of switch them with respect to each other. And then we are going to, this doesn't let me go down to a size 2 problem, but we're going to pause here. The towers of Hanoi size 3 problem is paused at line 12 because we haven't solved it yet. So pausing there, making a new instance of Hanoi, size 2. But now we have so this is equivalent to the size 2 problem. So from this perspective, this is our from, this is our helper, this is our 2. We're going to make a new version of this problem where we are going to be trying to move just these 2. Now, when we made this call, we said that we're swapping these rods. So we're trying to, from this perspective, get these 2 rods here. This is now our from, our 2, and our helper. So we're going to start back over at the beginning, asking, is this problem of size 1? No, it is not. So we're going to skip this and move down to line 12. We are now going to say, we're going to solve the Hanoi of problem size n minus 1. So we're going to put a pause on this, and we're going to make a new instance of this, size 1. And from this perspective, this is the 2 rod, this is the helper rod, but the old helper rod is going to be the new 2 rod. So this is now, from this new perspective, this is the helper, and this is the 2. Coming back in, we're putting this one on pause at line 12. So this is paused at line 12. This is paused at line 12. Coming to this problem, is n equal to 1? Yes, we're in the base case. So we can print out the very first thing we see. Take disk 1 from rod, and it tells us to go from the from rod to the 2 rod. So from this perspective, this is the from rod, it's still the from rod, and this is the 2 rod. So it's saying move from A to C, which is exactly the first print that we see. And this is how deep we are in the code when this first line is printed. We're all the way down the recursive chain already. There are 3 instances of this function up and running. Okay, we completely successfully did this. Now we have successfully moved this from here to there, which will be true in all of these because that's the instruction that was printed. So now we know that we've successfully moved this here. Well, now we need to figure out what to do next. So going back to this perspective, so this instance ends, we have successfully made this move. We're going to continue this process. Now, this has been moved here, right, to the helper rod, because it's the same rod. From this perspective, now that's the helper rod, not the 2 rod anymore. So, beginning back at line 12 here, this says we completed this. Now we need to take disk n, since this is now, we've now completed the entirety of moving the small triangle. From this perspective, the small triangle was size 1. Now we're going to move disk n, which is disk 2, from rod, and it tells us the from rod, to rod, the to rod. And from this perspective, this is the from rod and this is the to rod. So we're going to move this from here to here. So we make that switch. But now we need to make the line 15 call. So we're going to pause this iteration on line 15, and we're going to open up a new instance of Hanoi size 1. But it tells us now that the from rod is the helper rod. So this is the new from rod. The to rod is the to rod. So this is going to stay the to rod. And the helper rod is the old from rod. So this is from, this is to, and this is helper. Launching this version of Hanoi. Is n equal to 1? Yes, yes it is. There's only this one instance on the from that we need to move to the to. So we're going to take this from the from rod and move it to the to rod. So we take this and we move it on top of that. So we see that print. That is, we already did this, sorry, I forgot the check mark. And now we're printing the third one. We're back at depth 3 as we print this instruction. Since it was a base case, we return, having done nothing else of interest. We've now moved this onto that. And you can see that now we have 2 and 1. That's not a very good small 1. There we go. And these aren't here anymore. So since this was done, this was on line 15. That is the last line of anything we have to do from this perspective. This depth 2 problem is now solved. So this goes away. And when we're back in this land, this perspective, this is what we've seen. This is where we are in the problem. So this was paused at line 12. So we're going to continue from line 12 here. And now say take disk from the from rod, disk n, and from this perspective, this is disk n, disk 3, and we want to move it to the to rod, which is now we take it. So we make that process, and then you can see that we still have work to do from this perspective because we still have all of line 15 to go from this perspective because we haven't paused at line 15 yet. And that's going to move everything that was here back here exactly how we moved it to get it here in the first place. So we're breaking down a problem of size 3 into problems of size 2. We need to solve it twice. For each problem of size 2, we need to solve a problem of size 1 twice. Which means that for every time that we increase the size by 1, we're doubling the size of the problem. And if you see the minimum moves required to do this, it is doubling plus 1, doubling plus 1, doubling plus 1, doubling plus 1 every time in its size and the minimum moves that is required. So this solves Hanoi. It's a very nice solution to it. You can see that it takes almost no code, but what that code is doing is actually quite complex underneath the hood when you go run it. So you can do a lot of work with very little code. If you intelligently break the problem down into, there is one algorithm here that is underlying this entire process. It just gets repeated, 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 repeated as you solve problems that are slightly smaller, slightly smaller, slightly smaller. So you're breaking down a large problem into smaller problems, solving the smaller problems, and then combining those solutions into the larger solution to the larger problem. And that is recursion in a nutshell. This is the most complicated example that I'm going to go over, but again, I wanted to motivate. We saw how long the code was for an iterative version of this. And this is so much cleaner. And it allows you to solve large Hanoi problems very quickly. Any further questions on this? Does that make sense? Do we feel like we understand what this code did, even if I think that coming up with that code would still be a challenge. I don't really expect that at this level, coming up with something like this is intuitive. I'm just hoping that I'm justifying, well, given that we were able to write it, why does it work? And why is it better than iteration for this particular problem? If you have an understanding there, I think you're in a good place. How do we feel? We feel like we understand this is a bit better. Yeah, this is about what I would expect. I don't see perfect understanding from most of the class. But I also think this requires practice in order for this to feel more natural, in order for it to feel like a skill that you have as opposed to something that you've seen before. Okay, let's talk about the analysis of recursion for a little bit. I did talk about tailed recursion as we were going through this, but I wanted to give you an example of it. So we've talked about just about everything in this slide deck, just naturally as we've gone through it. So I'm mostly just going to reveal it, talk about the main points, and the main reason I'm showing it to you is the example of, I want to show you a tailed recursive factorial and what needs to change to make it tailed recursive. So to refresh your memory on tailed recursion, the big downside of recursion is that if you have a large number of functions on the call stack, you get a stack overflow exception because we just don't have enough stack room for all of those calls. So if you want recursion to emulate exactly what a loop is capable of doing, you need a way to structure the recursion such that when you go call the recursion from the perspective of this function, it's over, it's done. So to do this in factorial, let's take a look at what it would look like. If you can recall our factorial implementation, we basically just said, if the value is less than or equal to 1, you want to return n. And otherwise, you want to say, you want to return n times the call to factorial with the parameter n minus 1. To make it tail recursive, you need to use what we call an accumulator. We're going to keep track of the answer as we go. Instead of the person in line saying, I don't know the answer, and I'm going to wait for the person in front of me to return with an answer to a smaller problem, you're going to do the work and pass along the partially computed answer to the person in front of you. Say, hey, I'm trying to compute 5 factorial. I know that 5 factorial is 5 times 4 factorial. So I'm passing you the partially computed solution 5. And could you calculate 4 factorial for me and then multiply the answer by 5? The person who's next in line says, okay, I'm going to calculate 4 factorial. I know 4 factorial is 4 times 3 factorial. But instead of being done there, I'm going to take the 5 that the person passed from behind me. I'm going to say, I'm going to take 5 times 4, which is 20, and say that the result of 5 factorial is 20 times 3 factorial. Now, when I pass along to the person in front of me, I'm going to pass along those two numbers, the partially computed solution, 20, and the new problem, 3 factorial. And you can see that once we get to the front of the line, the person who's calculating 1 factorial, they know the answer. There's no need to pass back to the front, to pass back to the person who asked the question. They can shout the answer and everyone in line knows the answer, or publish the answer on the internet, or maybe we're all in a group chat and they just post the answer somewhere. And now the person who's curious in line can go check it. But we don't need that line of communication. In fact, once the person says, I'm curious what 5 factorial is, they can ask the person in front of them and then leave the line and go on with their day. Because the person in the front is going to publish the answer. They don't need to be around to see the answer anymore. So that's equivalent to on the call stack, we can get rid of that function on the call stack. It can just leave the line and go off and free that memory because we don't need it anymore. So There is one annoyance, and we've already talked about the annoyance with this implementation, and that's that there's an extra parameter. So whenever you're introducing some kind of tail recursion, you want to have this overloaded function with a public and a private. The user calls the public calls the private with the extra parameters. So here would be the public method that the user actually calls. And you can see that what we do is we just return the call to the private version and add in the extra parameters that we need. It becomes a really useless initial product if you make the user say a product starts at 1 every time they call a factorial function. So we again just don't make the user think about it. So whoever asked you to write this code calls the public method, never needs to know that the private one even exists. From their scope, from their view of this code, the public method does all the work. And now it can calculate factorials larger than what would cause a Stack Overflow exception. Unfortunately, Java still really doesn't allow for this, but other languages do, especially functional languages. So we're going to dive in and start talking about how to analyze recursive problems and the complexity of recursive problems. So we'll start with this concept. We have a recursive function. How can we figure out its complexity? Any ideas for this? If you've heard of recurrence relations, hold on to it for just a second. If you have not, how would you come up with a way to understand the complexity of a recursive solution, recursive method? Just like with code before, we analyze the complexity of every line. Our goal now is not to come up with a complete solution to the complexity of the method. It's to come up with the complexity of the method with an unknown variable in the middle of it, and that variable is that same method, that recursive call to the method. So we're going to write a function for the complexity of the current call based on the future calls to that method. And then when you unfurl this, you start to get a pattern that becomes something that you can relate to an actual mathematical function. So we're going to be doing it in terms of the number of operations required to solve this problem, and then a variable for the number that is required to solve the smaller problem. This makes way more sense with examples. So factorial. We are going to use this concept T of n. T of n stands for the complexity of this function with respect for a size n problem. And now we're going to relate this to the complexity of a problem of size n minus 1, because that is the size of the problem for factorial that you call. 5 factorial is 5 times 4 factorial. So it's a number of operations to break the problem down into a problem of size 4 factorial. But it is a constant number of operations. In fact, it's a single operation to be able to break the problem down like that. You're returning just n times fact n minus 1. I'm not using the tail recursive version of this for now. But it's a single multiply once the call is finished. So there's a single multiply that you do, and then you have to solve this unknown size problem of size n minus 1. We also need to specify the size of the base case. So how complex is it to solve the base case problem? Well, calculating 1 factorial is constant. We return 1, that is a single operation. So with this information, we can state to break down a problem of size n into a problem of size n minus one, that involves one operation. But now we can state T of n in terms of T of n minus two. Right? So we can say something like, let's actually unfurl it. If we can say T of n equals T of n minus one plus one, now can we make an equivalence that says, what is this in terms of T of n minus two? We just make a direct substitution of n for n minus one. And this allows us to say that this is equivalent to T of n minus two plus one plus one. I'm leaving it as plus one right now because we want to see how many of these there are. And this allows us to continue this process every time we add one and decrement one inside of here. At the end of this process, eventually this is going to reach T of one, which we know is one. Once we have that process, how many plus ones are there going to be in this expression? Yeah.
Wouldn't it be? Or it would be however. Sorry, I had a thought.
Yeah, I think you're on the right track. I think I can tell where you're going. It is right. Anyone else able to verbalize it? Yeah. It is exactly n. Yeah. So substitute 5 here. We would end up T of 4 plus 1. Let's actually write that out. We'll do even T of 3. T of 3 equals T of 2 plus 1, which is equal to T of 1 plus 1 plus 1, and we can make now a direct substitution because we know T of 1 is 1. So now this becomes 1 plus 1 plus 1, which is 3, which was the n that we originally plugged into here. And you can see that no matter what we plug in here, when we unfurl this, we're going to have exactly n ones. We do this for T of 4, we're going to end up with 1 plus 1 plus 1 plus 1. So this tells us that this function operates in, really it's theta of n, but I'm going to write it as O of n, but it is a linear problem. The linear solution to a factorial problem. This scales linearly with respect to, but we have to fully unfurl it to be able to see how this grows with respect to that. Questions on this? Does it make sense how I get linear from breaking this down, analyzing it, unfurling it, and kind of putting it back together? It'd be 1 minute, I can at least get you thinking about the next one. So Fibonacci's kind of gross. I actually want to do one that we know the answer to real quick. So binary search. We know the answer to this because it was on our homework. What was the answer to the complexity of binary search? Log of n, yeah. Yeah, we're breaking it down in half each time. But now, how would we solve something that is binary search? We have to solve a problem of something that is T of n. How would we come up with an expression to represent the equality? What is the size of the problem that is the result of a single call or a single, yeah?
Yes, was it n/2?
It is. Yeah, so the variable that's going to be present here is T of n over 2. How many operations does it take for us to figure out how many, or to be able to break down this problem into a problem that is half the size? It ends up being constant. It's the same amount of work depending on the size. So you can basically say plus C or some constant. You can make this plus 1 because we know that it's equivalent to it, but the idea is that it's some constant. So now the question is, what is the complexity of the base case? If we have an array of size 1, how long does it take to determine whether the query is in it or not? constant. So we're gonna say that T of 1 is 1. So now we can start unfurling this and coming up with a particular size. We have an array of size 8. Well, we can say T of 8 is T of 4 plus some constant. We could then say this breaks down into T of 2 plus C. How many C's are there going to be with respect to the size of this? It's the exact inverse. It's going to be the log of the size of this. So we can see that this breaks down into the log that we would expect when we solve this recursively, because every time we're breaking this in half and adding 1. What do we know about logarithmic growth? On one axis, it's +1. On one axis, it's ×2. Dividing by 2, adding 1. Dividing by 2, adding 1. Dividing by 2, adding 1. That gives us that logarithmic guarantee. So we'll come back to this next week. Like I said yesterday, tomorrow I want to focus just on your last minute ape study questions. So come with those last minute curiosities and confusions, and we'll go over whatever you're curious about.
I think it's because I did it a little bit differently instead of having silver rod being an end thing, I had it be in the middle.